I'm really sorry, just give me one more second. Right. Hi, hello everyone. Welcome back to the class. Today's class we are going to be learning a few topics from electrostatics. So in today's class we will be covering from a topic from electric potential. Before that, we had actually in the previous classes we have covered electrostatic field due to a potential, right? Because of what is the field in the axial line and the equatorial plane. We have done that. So today's class we will go with torque experienced by a dipole on a uniform electric field, right? That is where we were going to start the top today's class with. So before that, my name is Mohana. I am a physics educator at Unacademy. So I'll be basically taking your class 11 and 12 physics. Okay, and also in case, right, so just a second, right, also you can follow me on my Telegram group, right? Before going live for any class, earlier itself I would have shared the link, right? All updates will be available for you from this link, so you can follow me on my Telegram group, and also you'll see some questions asked in pool style. For that you can follow the same, and also in the Unacademy ICSE and ISC board, right? This link is a common Telegram group link for both ICSE and ISC board. You can follow this channel as well. So just like how we have these special classes on the YouTube channel, right? Likewise, we also have some special classes on the Unacademy platform as well. So these classes, we usually call them as special classes, and you can take any of your favorite educators' classes for free. And again, you can engage with them, right? You can engage with all of these special classes has this feature called as pool. So you can engage with the educators through via pools, and these are just questions. You can learn a concept through questions. Some questions will be asked regarding concepts or even feedback for the class in terms of pools, and you can answer them through this, right? Then these special classes that's happening on the platform, they are also live special classes, so you can get your doubts cleared then and there. Now there will be a link in the description box, right? And you can use that link to go back to the previous class recordings, and what are the upcoming classes, special classes for class 12 will also be shared. And in case if you're not finding that, you can use my code MTIS10 to unlock all of the special classes that were previously recorded and as well as the upcoming special classes in the Unacademy platform. Now these special classes, the next special class is on 4th June around 4 p.m. Okay, all special classes are around 4 p.m. 4th June 4 p.m. and the topic will be pull to magnetism. So basically we are going to study some concepts from magnetism, from the unit of magnetism. So this unit we will be studying from the basic chapter 1 of your first concepts, right? We will be learning from the basic concepts of magnetism, okay, from your unit 3. This is what we'll be covering. The next class that is upcoming is around 4 p.m. again, but this is on 11th June around 4 p.m. and this class will be about current electricity. Okay, and the class after that would be on 14th June, right? This is again at 4 p.m. and this will be again pull to magnetism. Okay, and this classes will be so basically if you see here on the OIT platform, we are covering unit 1 and I'll be starting unit 2 also very soon. Okay, and at the same time in the app also, for the special classes also, I am doing unit 2 and as well as unit 3. So you can cover 3 units in this month. All right. Now the features, in case if you're taking the plus feature, So there are various advantages for your for the Plus subscriptions. One is you can learn from the comfort of your home. Then you get unlimited access to all the courses. So if you take any subscription, any Plus subscription, right? If you're taking ISC Class 12 subscription, so you'll not only get physics, you'll get math, chemistry and biology as well, okay? And all the educators on the platform are good, so you'll be learning from the top educators. Now, one of the features in the special classes is that we have a regular doubt clearing session. So if a course starts today, every 4th session will be a doubt clearing session. So in the doubt clearing session, right, we will usually be for the past 3 classes, whatever you learn, if you have any doubts, we would be discussing about those concepts on these doubt sessions. Now in the Plus class, we would be exhaustively covering, right? We will be covering the entire syllabus. Now we also have live test series. So every alternate week we usually give live test series. So in the live test series, if you whatever concept you're learning, based on that, if you're taking a live test series, you would actually understand whether you understood the concept or not, right? So after the test, there would be an analysis session, and you can actually ask any doubts you have also any doubts you have regarding the questions you attempted. In case if you made any mistakes, you can correct them, and in case in case you want to know how to solve that question easily, also you can ask the teacher or ask the educators about the same. We are coming up with new courses, right? So do check out. Then the course per if in case you're taking the duration of the course you're taking, right? If you're taking a course for a longer duration, the price per month reduces. So for example, if you're taking the course for 12 months, right, 1 year, then the price per month becomes 1438. Okay, now you can use my educator code. This is price per month, right? As you take longer duration, the price per month reduces, and this is the price per month you're paying, right? 1 month you're paying 1438. If you're taking 1 year subscription, this is the amount you're paying. This is for all subjects: physics, chemistry, math and biology as well. Now you can use my code MTIS10 to avail a 10% discount on the same. On that, you can get the course for 1294 per month. So this is in case if you're taking a 12-month subscription. Okay, so that's a year subscription. So other months like 9 months, 6 months and 3 months is also there indicated. Okay, and now the Unacademy Unset, this is basically Unacademy National Scholarship Admission Test is going on. You just have 4 more hours for this registration to close. So in case if you're planning to take your, if you want to take Unacademy's IIT JEE courses or NEET courses, right? Or if you're in class 9 and 10 and if you're looking for foundation courses, this applies for all of you. So this test will be a computer-based test, but in the offline centers of Unacademies, right? It happens around 40 cities, and the test last day to register the test is June 2nd, that is today. So you still have 4 hours, right, left to register. So if in case you're planning to register, now would be the best time, right? And the course price is 199 rupees. Now again, if you're using my code MTIS10, you'll get a 10% off, right? The top all test takers will actually get an Unacademy t-shirt. The top 40 rankers will get a chance to win an iPhone. And if in case if you're taking up to 49, you have an option, right? Depending on how much percentage you're getting, right? You can win up to 90% scholarship, okay, for Unacademy centers and offline subscription. If in case you're taking these courses in Unacademy platform, or in case if you're taking them in the offline centers of Unacademy, right? For both, this scholarship applies. Okay, the test will be on June 4th and 9th. If you have any queries, you can ask me in the chat box, and I'll be happy to answer. Right, so we learned a lot of concepts, right? From the beginning, we learned what is an electric field is, right? And Right, so if you have any of the doubts in any of the concepts we have learned till now, you can again ask me in the chat box, right? Or in case if you're watching, the recordings, you can actually drop in, you can actually ask me in the upcoming classes in case any of the concepts are not clear, right? So electric field is very simple, okay? If you take any charge, right, the electric field is just defined as the electrostatic force. Electric field is just defined as the electrostatic force per unit charge, right? That is basically your electric charge, and this is given by electric field is basically given by Newton per coulomb, right? This is given by Newton per coulomb, and the electric field lines are, again, if you are looking at the equation for this, this will be 1 by 4 pi epsilon naught, right? Q divided by r square. Let's say let this be the test charge Q naught, then this is the source charge Q divided by r square. So this bit we have already done in the previous classes. So if you have any doubts, you can ask me, otherwise I'll move forward. Now this is electric field is a vector quantity, okay, and for a positive charge the electric field lines are always pointed radially outwards, and for a negative charge electric field lines are pointed radially inwards. Now in general we usually imagine the charge to be spread in a continuous manner in any region of space, okay. Now such charge distribution is known as your continuous charge distribution. Now there are three types of continuous charge distribution. One is volume charge distribution, another one is surface charge distribution, another is a linear charge distribution. Now charge per unit area, when you're talking about charge per unit area, then you're talking about surface charge distribution, okay. Then charge per unit length, that is one dimensional, in a wire, right? How many charges are there in a particular region, okay. That is charge per unit length. When you're talking in one dimensional, then it becomes linear charge density. So surface charge density is two dimensional. Now charge per unit volume, right? Charge per unit volume, when it's three dimensional, it is basically a volume charge density, and it's three dimensional. It's your charge per unit volume, okay. Next, we also learnt about what are electric lines of forces, right? Now any region around the charge has electric field lines. To understand the electric field lines better, we introduce the concept of electric lines of forces, right? Now the electric lines of forces, they are imaginary smooth curves, right? They smooth curve drawn in an electric field, okay, along which a free isolated point charge could move. So if you have a charge moving in this direction, at each point if you're drawing a tangent perpendicular to it, right, that will basically give you what is the direction of this electric field lines at every point, right? So the electric field lines, electric lines of forces are not real, but the field they exhibit is actually extremely real, right? The electric field lines are real, but electric lines of forces as such are the electric lines of forces that we are seeing are basically not actually real, right? These are imaginary charges, right? So next we would see what would be a positive charge. For a positive charge, the electric field lines are always pointed radially outwards. They start at the start and they end at infinity, right? Similarly, for a negative charge, the electric field lines are pointed radially inwards. They start at infinity and they end in the charge, right? Now what would happen if you take two charges, okay? If you take a positive charge and negative charge, now whichever lines over here that were radially pointed outwards, right, electric field lines that were radially pointed outwards, now they bend, right? They start at the positive charge and end in the negative charge, okay. So these were the topics we covered in the previous classes. So I'm quickly going through origin, right? So electric field lines start at the positive charge and end in the negative charge, right? Now if you take two equal and opposite charges, so if you take two charges, they are equal in magnitude. For example, if this is minus 10 microcoulomb, this will be plus 10 microcoulomb. Two charges equal and opposite, and if they are separated by a distance, let's say the distance of separation between them, most of your textbooks takes it as 2L or 2A, right? That is from here, right? For example, this is minus 7 microcoulomb of charge and plus 7 microcoulomb of charge, okay? So same charges, but one is a positive charge, another is a negative charge. Now from here to here, right, from here to this midpoint over here, we can say this distance is basically A, right? From here to the midpoint of the charge, again, this you can say is A. So totally the length you're taking is basically 2A, okay? And this separation is also extremely small. So two equal and opposite charges separated by a small distance constitutes an electric dipole. So what it means is, Abhishek, hello Abhishek, right? So whatever charges, whatever field lines are basically coming out of, how many ever field lines that are coming out of the positive charge over here, right? Let's say there are 100 field lines coming from here, right? For a positive charge, the field lines are radially pointed outwards. A negative charge, it's radially pointed inwards, right? So if there are 100 charges that are coming, 100 lines of field lines are coming from the positive charge, right? All of them will terminate in the negative charge. And if you look at the shape over here, you can see this has a cylindrical symmetry. Okay, so this is your nature of the electric the electric dipole. So if you have a charge, right, if you have two equal, and Sanjit, hello Sanjit, if you have two equal and opposite charges separated by a small distance, then it constitutes a electric dipole. Okay, so electric dipoles in case in this case, right, so this is an electric dipole over here. Okay, all right. Okay, if you have any doubts, you can actually ask me in the chat box. Now, these electric dipoles, right, also has an electric dipole moment associated with it. Electric dipole moment doesn't do anything. It just measures the strength of an electric dipole. Okay. Now, the field due to this charge is always from positive to negative, right? The field is always from positive to negative. Right, this is the direction of the electric field lines in a dipole. Okay. Sanjit is saying positive charges goes outside. Yes, Sanjit, it does. Right, so the dipole moment just measure the strength of an electric dipole, and the dipole moment of an electric dipole, now this is a vector quantity. Okay, and if you want to find its magnitude, right, if you want to find what is the magnitude of this dipole vector, right, this dipole moment, that is given by either of the one charge. Okay, any charge you can take the magnitude of any one charge. Okay, why? It's a dipole. If this is minus 2 microcoulomb, this will be plus 2 microcoulomb. So you can take any one dipole moment, that is basically your this would be basically your this will be around 2 micro, let's say this is a charge q, any one of the charges, okay, times the distance of separation between them. What is the distance? Let's say from here to here, let's say the distance of separation between them is 2a. So from here to the midpoint a, and from midpoint over here is a, so totally 2a. Okay, then into 2a, the distance of separation between the two charges. Now this constitutes your electric dipole. Now why is it a vector quantity? Here this is a vector, right? This distance between them, this is the area, the position vector that you're giving, and here this p, the dipole moment, is also a position vector, and the direction of a dipole moment is always along the negative to the positive charge, and the dipole moment always wants to align itself with the electric field. Okay, that also. So in this case, in case if it's kept in an external electric field lines, all right. So the dipole, the charge, electric field lines always go from positive to negative charges, but the dipole moment direction is always from the negative to positive charge. Okay. So this part we have covered in the last class, and we've also seen what is the field lines due to the electric dipoles, right? So if you basically see how the strength of this electric dipole, right? If you want to see what is the strength of this electric dipole, dipole field, right, when compared to the radial fields. Right, that also we did, right? So the field lines here, the field lines at the axial, right? This point, if you're finding, this is your electric field lines at the axial. The intensity of the electric field lines in your axial is twice that of the intensity of the electric field lines on the equatorial, somewhere over here. So the field line here is twice the equatorial, right, plane. So this we have covered in the last class. Intensity of the electric field line at a point on the axis of the dipole, and also intensity of the field line at a point on the equatorial line of a dipole, we have covered in the previous class. You can check out that video. Okay, now what we are going to study in today's class is, these dipoles are very interesting simply because these exist in nature as well. Okay, so if they exist in nature, like for example, a water molecule is a dipole, it's an electric dipole. Okay, so if they exist in nature, then we say these are permanent dipoles. All right, Now it becomes very important for us to study these dipoles, because if you want to understand the properties of this water, right, water molecule, then you have to, then if you want to understand, right, so to understand about these water molecules, you have to study the structures and everything, right? So dipole moment, studying about these dipole moments becomes extremely important. At the same time, these dipole moments are what, right? The dipole moment is, since water molecule is a dipole moment, and if I take this dipole and keep it in an external magnetic field, okay? So what we are going to do is, we are going to take this dipole, right, this particular dipole, right? If I'm taking this, it has its own magnetic field, okay? Positive and negative charges between strong forces, okay? All right, Sanjit, could you please explain what you're trying to tell me? Positive and negative charge between two strong forces. Electrostatic forces are stronger than your gravitational force, right? And in this case, because the charges between them is positive and negative, the type of forces is over here is basically an attractive force. Now, if you take this dipole, if you take this particular dipole, and if you keep them in an external, okay, magnetic field. So you're taking this entire dipole and you're keeping them in an external magnetic field. Okay, it has its own magnetic field. It's not like not, it does has its own magnetic field, but we are going to take this and keep it in an external magnetic field. Now the external magnetic field is not, in this case, it is a uniform magnetic field. If you see, the field lines are more or less equally spaced, and if you see, if they are in the same direction, they're all going in the same direction. Now this is a uniform electric field. Now we are taking the dipole and placing this in this uniform field. Now question arises, why should we do this? Why should we learn about what happens to a dipole when you're keeping it in an external magnetic field? Turns out your microwave oven works on this principle, right? The food contains water molecules, and these water molecules, when you keep them in a varying uniform electric field lines, they tend to experience a torque and rotate. Okay, now because of which because they are experiencing a torque and it is rotating, right, it heats up our food, right? So let's see how that happens. Now when you place them in an electric field line, right, if you keep them in an external electric field line, now you're keeping it at an angle. So you're basically keeping it at an angle theta, okay, and let's say you're keeping it with the external field line, right? You're basically keeping it at an angle theta, and the distance between these two is basically 2a. From here to here it is a, from here to here it is a. To get to totally together, the distance between these two charges is basically 2a. Okay, now the direction of the dipole moment would be in this direction, right, from negative to positive. Now as soon as you keep them in the external magnetic field, what would happen? The charge, we know, how did we define, right? What will be the force experienced? Okay, now this is the positive charge q, right? This is plus q, this is minus q, right? And you take the dipole and keep it in an external magnetic field, then what will be the force experienced? The force experienced on this charge over here, this is given by this equation. This electric field lines is equal to force per charge, right? Now from here we can say, what is the force experienced on this charge, positive charge, when it's kept in the electric field, right? Where it will be the force experience, that will basically be Q into E, right? Now what will be the direction in which it will experience the force? The direction in which it's experiencing the force, it will be in this direction, right? It is, so if this is basically an electric field, right? So if it's an external electric field lines, which means there is a field line over here, this should be the positive side, this will be a negative side. Why? Because field lines are always going from positive to negative. Field lines are going from, in this case what will happen, positive to, field lines are always going out from the positive charge, right? It's always pointed radially outwards, and in case of a negative charge, it's pointed radially inwards. So this should be the direction. So what will be the force it is experiencing? This side is positive, so this is a positive force. So here it will be repulsion, so it will get attracted towards this direction. The force experienced by this charge, right? This positive charge would be in this direction. Okay. Similarly, what will be the force experienced by this charge, right? Now the force experienced by this charge is again given by the same equation. So in this case, it will be minus QE, minus sign being just to indicate that it's a negative charge, and this plus sign being it is just a positive charge. But what will be the direction in which it is moving? The direction in which it is moving will be in this side. Why? See, this is a positive side, right? This is negative. So radial, the force, this charge will get attracted towards this direction, right? How do we get the external magnetic electric field is only we have given, right? So we have two plates, and through which we are giving an external magnet electric field lines are generated, right? So this charge will experience a force of attraction, right, towards this side. This charge will experience a force of attraction towards this side. All right. So if you have any doubts, ask me. Otherwise, I'll go ahead with the explanation. Okay. So here the force experienced will be QE, and here the force experienced will be minus QE. Okay. Now, there are two different forces, right? But there's the same force. Okay, they have the same magnitude, but it's acting in opposite direction, right? When a force acts on an object, right? When a force is acting on an object, right? But it's acting in such a way that it has same force, but it acts in the different direction. Then it will constitute a couple, right? That in turn what will happen? This force, this whole dipole will experience a torque, and because it torque, and it will start rotating. What is the direction in which it will rotate? Now that will basically be given by the direction that will basically be given by the dipole moment, right? Now the dipole moment goes with the negative to positive charge. Now the dipole moment always wants to align itself with the electric field lines. So it will start rotating towards this side. It will start rotating towards clockwise. Okay. So now this dipole experiences a torque. Okay. Now initially, as it rotates, okay, this is the angle theta, right? As this dipole rotates, right? As this dipole rotates, there are two things that will change. Right? One is this angle theta will basically change, and then this length. This length talks about the distance between these two charges. The distance between these two charges is basically given by this length over here. Okay. As the distance between these two charges, decreases, this length again will keep decreasing. Right. So see, as the dipole rotates, this length over here, angle also changes. Angle theta also changes. So is this length over here, right? This also changes, right? Let's take this length as L. Okay, or we can take it as X, right? Let's take this as X. Okay, and this length actually keeps reducing, right? So if it is reducing means what is happening? It is slowly this is as it reduces as it turns, right? As it experiences a torque and as it rotates in the external electric field, this length over here keeps reducing, right? Till when? How long will this torque apply on this dipole over here? Okay, the torque experienced by this dipole will be till the dipole moment, right, aligns itself with the electric field line. Okay, now there's no angle between them. The distance between them is also not gone, right? There's no angle between them or distance. Now it's just there is two forces acting on them at two different directions. Equal forces acting on them at two different directions. Now this dipole has reached a stable position, and it will no longer experience a torque, so it will no longer rotate. Okay, right? If you have any questions, you can ask me. Otherwise, I will keep solving. Right now, here, if you look in this system, if you look at the total force acting between these two charges, right? What is the total force acting between two charges? This is the force acting, right? Because of the positive force, it's in one direction. Because of the negative force, is in one direction, right? So if you look at the total force, these two forces are equal and opposite. But this is basically so the total force, right? Total force is 0 in case of translatory force. Okay, a translating force on a dipole is a force. If you apply a force along the center, right? If you apply a force along the center of the dipole, and if the dipole is just moving in its field, then we say it is a translating force. Okay, the net translating force on this dipole is 0 because this side and this side equal forces, right? Opposite, and it's acting in opposite direction. But it experiences a torque because same force acting on the same on the same object, right? On the same object over here, two forces are acting in different direction. So that makes this charge, that makes this dipole rotate. Okay, so as this rotates, it experiences a force, right? Let's calculate what is the force it experiences. Okay, so that's given by the torque, right? So torque, we actually say, right, is given by, torque is basically given as, right, to experience torque we give it as tau, right? Torque is a product of either any one of the force, right? We are not worried about the force acting on the positive charge or the negative charge. Force acting on either one of the charge. Why? Because the magnitude is the same. Okay, force acting on any one of the charge, the force acting on any one of the charge is over here is basically QE, right, times the perpendicular distance between the charges. What is the perpendicular distance between the charges over here that we have taken? That is this. Between these charges, between these two charges, the perpendicular distance we have taken is this x. Okay, so torque is any one force, any one of these forces times this perpendicular distance. How much force is applying, right, per the, how much different distance this is covering. So that's the torque, right? Now, so that is basically given as, here torque is given by any one of the forces, any one of the forces. So force is given by Q into E, right, into what is the perpendicular distance between the two forces. That perpendicular distance between the two forces is basically given as x, right? Now we have to actually find out this quantity. What is this x over here, right? This quantity we need to find out. Now how do we get that particular quantity, right? We want to find this one, right? We want this one, so somewhere we have to take hypotenuse into account and this one, right? This is your perpendicular by hypotenuse or your opposite by hypotenuse, right? That is given by sine theta, right? Sine theta is nothing but this x, right? This angle theta, if you consider, sine theta is equal to this x, right? This distance x by what is this distance over here? 2a. From here, what will be x? X will be 2a into sine theta. Okay, so we have found the value of x from this. So let's substitute that in the equation. So this tau, right? This is either one of the forces. So initially we just had to give for any one of the forces. Force could be because of positive or negative charge, because magnitude is same, direction is different, right? So let's substitute over here. What is any one of the force? Any one of the force is given by Q into E times what is the perpendicular distance between them? That we found as 2a into the terms of angle, right? Sine theta. Now we also have seen earlier, right? What will be this? From here actually we can see the dipole moment. The dipole moment is given by either one of the charge into the distance between them, right? This is the dipole moment. Because of this, now this equation changes. Now this becomes as, right, this will be basically Q into 2a. Q into 2a is your dipole moment P into E into sine theta. Okay. Now the direction, okay, of torque, right, is basically perpendicular. The direction in which this torque is acting is basically perpendicular to these two, right? The over here, if you see, the dipole moment is basically in this, right, over here, right? So the dipole moment is always from negative to positive charge. So dipole moment is in this direction, and the dipole moment is in this direction. Okay. Where is the field acting in? The field is acting in this direction, right? This is for the dipole moment P, and this is your field E, right? This is your field E. Now this between the dipole moment, okay, the angle between this dipole with that of the uniform electric field line, right? That angle is theta, right? This is the angle. Now, and the dipole moment always wants to align itself with the electric field line. Now, what will be the direction in which the force is acting? The force is acting down. It's acting clockwise, right? So the force is acting in this downward direction. The torque is acting in downward direction. Okay, and over here, if you look at this equation over here, right? Now, what is aligning itself, right? So we have from here we have, right, this is your dipole moment direction, this is your electric field direction. Your torque is basically applied in downward force, right? Now, this is basically to find your magnitude, you can use this torque equation. But this torque that is applied, that you're seeing over here, is a vector, right? So how do we write in vector terms? So if you're seeing how to write in vector terms, then this tau is equal to sine theta, always comes for cross product, right? So you can write it as P cross E or E cross P. So this is where you need to take into consideration here. The electric field lines are not changing to align itself to the dipole field, but the dipole field are changing to align itself with the electric field lines. So here the total torque will be P cross E. If the electric field lines, because the dipole moment, right, the dipole moment is basically turning to align itself with the electric field lines. So in vector equation, this becomes tau is equal to P cross E. Okay. Right. So this gives you the vector. This gives you the vector equation. This gives you the magnitude of the torque experienced by the electric field lines. All right. Now, why are we, once again, to say why are we using it? The basic idea of your microwave oven comes from here. So if you have if you keep changing the magnetic field lines, the electric pole will, the electric dipole will want to align itself with the electric field lines. Why? Because it feels this is the equilibrium state, right? This is when the entire dipole becomes stable, right? But whichever angle you're keeping, right? If the angle is bigger or smaller, right? If you keep it at a particular angle, what happens? It rotates, it experiences a torque, okay? And the torque would actually reduce till it comes to this state over here. Okay, so from here, if you keep tilting the electric field lines, if you keep changing the electric field lines, your dipole will basically rotate, which is basically the basic principle behind your ovens. Okay, now there are three special cases for this. So first special case is when do you get a maximum torque? Okay, so the maximum torque you can get over here is for sine theta, right? Theta is basically the deciding factor over here. So if the angle is more, so sine 90 means sine 90 is 1, which means you'll get maximum torque. So the first case when you'll get maximum torque is when the dipole is kept perpendicular to the field. In this case, what happened to the angle over here? The angle becomes 90 degrees. Okay, and we know torque is basically given as PE into sine theta, right? So from here we can say this is PE into sine 90 degrees. Sine 90 is just 1. So you get P into E. So you get maximum torque when theta is equal to 90 degrees. So when when basically your dipole is kept perpendicular to the field, then you get a 90 degree, then you will get the theta to be, sorry, then you're basically getting the theta, right, the tau is equal to P into E. You get maximum torque for theta equal to 90 degrees when the electric dipole is kept perpendicular to the field. Okay, next, when do you get, there are two cases in which your dipole is basically minimum, or we can say the dipole is actually 0. So the first case is basically, you can say tau minimum or 0 when there is no torque experienced by this minimum, or in this case there is no torque experienced by the electric dipole when the dipole moment is aligned with the electric field lines. In this case, if you see, there is no angle between them, right? If you see PE sine theta, there is no angle between them, right? This theta is basically 0. In this case, theta is equal to 0, right? Theta is 0 means you will get, okay, this will basically be theta tau minimum, or this becomes 0. This becomes 0. So which means there is no torque. Okay, so this position where there is extremely no torque, where the magnetic field, where the magnetic dipole moment is completely aligned with the electric field lines, right, is what we called as a stable equilibrium, okay, or the stable position for the dipole. Now there's one other case where you can get a minimum dipole, or you can actually get a the dipole moment is minimum, or there is the dipole moment we say is basically zero. There is no torque experience. There is no torque experienced by this electric dipole. The second case is when these charges are actually 180 degrees. See the difference? In this case, positive is going this side, negative is going this side, right? Negative charge and positive charge, if they are flipped, if you turn the dipole 180 degrees, right? Now this side also, this you see no torque only. In this case, what happened? You have PE sine theta, right? Now in this case, theta is equal to 180 degrees. So sine 180, what would be sine 180? What is the value of sine 180? Right, sine 180 is again 0. Right, so from here we can say that your torque, right, this sine 180 is again 0. So here there is again no torque, okay, but this case is not a stable state like the previous. This is a stable place. This state is basically very extremely stable, but in case of this position, this is of extremely unstable position, okay. So even if you rotate this dipole even by a very small amount, this dipole will turn entirely, and the magnetic field lines will align, okay. This will again turn entirely around, and your positive charges will come towards here, experiencing a force on this side, and your negative charge will actually go here and experience a charge in the next in this direction. Why? In this case, because this is the stable equilibrium. This is the position the dipole prefers to be in. Now in this case, if you see, P is acting in this direction, electric field lines are acting in this direction, the angle between them is 180 degrees. Okay, so so this is another state, right? Another special case. So this is the case when the dipole has this is in as in an unstable equilibrium position. Okay, now these are the three cases of these are three cases for the electric field experienced by a dipole. Okay, so from here, okay, when you get the maximum torque, you get the maximum torque when the electric dipole, right? When the electric dipole is basically perpendicular to the field, you get the maximum torque, right? Sine 90. Sine 90 is basically 1, right? So this so which means it has to turn, the dipole has to turn 190 degrees, sorry 90 degrees, right, to align, then come on to, then it will align itself with the electric field line. So tau max, from here we get basically this is basically maximum, you get PE sine theta, right? In this case, when do you get maximum torque? When theta equal to 90 degrees, right? So right, so you get this maximum theta. For theta equal to 90 degrees, you get maximum torque. So tau max will be equal to P into E. Correct. So from here, okay, from here, if we just say, right, so if we just say that from here, if you want dipole moment, you can say that is the maximum torque experienced by the electric maximum torque experienced by the dipole by the electric field. Okay, now from this equation over here, let's say my E is basically 1 unit, my electric field is basically 1 unit, and let's say my theta is equal to 90 degrees. Okay, then what happens in this, to this equation, right? My E, now this similar thing, we are just going to see that we have torque is equal to PE sine theta if E is equal to 1 unit, okay, and theta is equal to 90 degrees, right? Then from here we can say that tau is equal to PE, E becomes 1, sine 90 is 1, so you'll get the torque is equal to the dipole moment. From here we can define the dipole moment. Okay, the dipole moment can be defined as right, the dipole moment may be defined as on an electric dipole torque, may be defined as the torque acting on an electric dipole, okay, placed perpendicular, because when you place the electric field, when you place this charge perpendicular, when you place the electric field line perpendicular to the field lines is when you will get theta equal to 90 degrees, right? Placed perpendicular, right, to a uniform. What is the strength of the uniform electric field and what is the strength of the electric field? It's basically 1 unit, right? So electric field of unit strength. So that's another definition way you can define dipole moment. Not just as force into the separation between the two charges, but dipole moment can also be defined as the torque acting on an electric dipole placed perpendicular to an unit electric field of unit strength. Okay, so this is basically we have covered the torque acting on a electric dipole, okay, when it's kept in a uniform electric field. If you have any doubts, you can ask me, or else I would be covering, or else we'll learn about what is an electric potential. Okay. Right. So the electric field around the charge, right? There is a charge, the electric field around the charge can be described, right? Electric field around a charge. Electric field around any charge, this you can actually describe by two ways. Okay. One is through the electric field. Okay, one is the electric field around a charge, okay, around a charge can be defined by two ways. One is through its electric field lines, right? One is through its electric field line E, right? Another way is through their electrostatic potential or potential difference. Or potential difference. Okay, this electrostatic potential over here, now this is a scalar quantity, right, wherein your electric field line is basically a vector quantity. So let's learn what is this electrostatic potential, right? Now both these two are characteristic properties of a charge, of a point, right, of any point in field, okay, and they both are interrelated also. Okay, now what is a, so there's two different things you're going to learn. One is what is potential difference and what is electric potential. Okay, both are same with just a minor difference. Okay, the electric potential difference, right? So let's say you have a point charge over here. Let's say there is a point charge over here. Okay, let's say this is my source charge, and this is a positive charge, right? So the field lines will always be pointed radially outwards, correct? So this field lines are pointed radially outwards. So this is the direction of the field line, right? Now now we are going to bring in a test charge. Okay, right, let this place be O. Now we are going to bring in a test charge. Okay, and we're going to place it somewhere over here. Right, now this is a test charge. This test charge is Q0. This is basically your test charge. Okay, test charges, unless and otherwise specified, is always positive. So this is a positive test charge, right, placed at the point A. Now what will happen to the force acting on it? It will repel, right, because this is a positive charge. Because this is a positive charge, over here what will happen? The force will be repulsion. So this will get repelled in this way. Now in case you're moving this charge from this A, right, to this point B, you're moving the charge from the point A to this point B, right, against this electrostatic force, right, you're moving it in this direction, though it's a positive charge, right, so you're moving it in this direction, right, though it is feeling a repulsion in this side, right, you're moving it in the opposite direction, okay, towards the source charge, right. Then if you want to do it, some work has to be done, right. So that basically becomes your potential difference. So potential difference between 2 points in an electric field, the potential difference between 2 points in an electric field may be defined as the amount of work done, okay, in moving a unit positive charge from one point to another against what? Against the electrostatic forces because of this source charge over here. The source charge will repel this positive charge in this direction, but despite that you're moving it from one point to another on this field line. So you're moving it closer towards the source charge. The work done in moving the unit charge, test charge, from one point to another is basically called as your potential difference. So now that we have defined what a potential difference is, let's write it in an equation form. Okay. Now what is the potential difference? Potential difference, we can give it by V. This is what? The potential difference at this point A is difference from the potential difference at this point, right? Because why? Electric field line, the strength of the electric field line drops as you go further away, right? So as you're going far away, the electric field strength decreases. It would be comparing to moving it here, no, moving it from here to here, right? At this point, how much work is done? If you have to move this from here to here, at this point you have to apply much more work, right? Much more work has to be done to move over from here. Why? As you keep going closer towards the charge, the field line or the intensity of the field line increases. At this point, the inductivity might be lower than at this point, right? So you're doing a work, right? So the work done or the electric potential at this point is different from the electric potential at this point. This point will be a little weaker when compared to this point. The closer you go towards the charge, the electric potential will be much more hard. Why? Because the number of field lines are more. So the work has to be done to go towards that, right? Against that electrostatic force will obviously be more. Now, this electrostatic, the potential difference V is given by what is the potential difference at this point, right? What is the potential difference at this point? That is VB, okay? Minus what is the potential difference at this point? That is basically VA. This is what? The potential difference. The potential difference, this is basically the amount of work done in moving a unit positive charge from one point to another. You're moving it from this point to another. Okay, the difference between them gives the potential difference of this place over here. Okay, now this is equal to what? The amount of work done in moving a unit positive charge from one point to another, right? Now work done. Okay, how are we going to write work done? Work done in moving a unit positive charge from A to B. Work done in moving a unit positive charge from A to B, right? So work done in moving a unit positive charge. That positive charge over here we are taken as Q0. Now this becomes your definition for potential difference. So one thing we are taking into consideration is when we are introducing the test charge inside over here, right? We are taking it to an account that it is not disturbing this field by the source field by any chance. Okay. Now, we also take into account the amount of external forces that is basically applied on this test charge to move it against the electrostatic force of repulsion, right? Because of the source charge, right? That particular force that you're applying just balances this electrostatic force. How much force you're applying to move this charge from A to B, right? That force should balance the repulsive force because of the electrostatic repulsive force because of the positive charge. Okay, so that this charge does not produce any, the test charge does not produce any acceleration. Okay, so this defines your potential difference. Now from here we can say what is the unit, what will be the unit of your potential difference, right? Though the unit of your potential difference is basically given by volt, right? The SI unit of potential difference is volt. So okay, so 1 volt, if you consider 1 volt, is nothing but what is the potential difference is given by work done, right? Potential difference, right? Potential difference is basically given by work done, right? Work done in moving a test charge from point A to point B, from one point to another in the against the electrostatic force of repulsion, right? Work done per charge, right? Per unit charge, right? Per charge, per touch, work done per charge. So what is the unit of potential difference? Volt. Volt will be equal to what? Work done is given by joules, right? So 1 volt will be 1 joule by 1 coulomb, right? So from here, right, from here you can say the potential difference between 2 points is in an electric field is said to be 1 volt if 1 joule of work has to be done, right, in moving a unit. 1 joule of work has to be done in moving a unit charge, right, from has to be done in moving a positive charge of 1 coulomb, right? The test charge taken is basically 1 coulomb from one point to another against the electrostatic force. That is basically 1 volt. Okay, so from here if you give what is your formula, right, you can give 1 volt is basically equal to right, so you can give it to 1, you can actually give it as 1 joules, right? So again this could be given as 1 Newton meter, coulomb inverse 1, joules in terms of Newton meter, or you can give 1 joule coulomb inverse 1. Okay, so this is basically you will learn more about this, right, how it is becoming Newton meter, right? The electric potential in terms of electric field, how you can electric potential, how you can define in terms of electric field, you will learn in the upcoming class. Now the electric potential, okay, let's say if the charge is somewhere at infinity, it's very, very far away. So if you're moving the charge from somewhere far away, which let's say you have a positive charge, let's say you have a source charge over here, right, let's say you have a source charge over here, right, and this is its sphere of or these are the charges, like field lines everywhere around, there's field line. Now somewhere over here if there is a charge, right, and if you're moving this charge into this influence of this electrostatic force, so at this point what is the field line in the electric potential, right? When it is far away, no point, right? It is not under the influence of this field lines at all, right? That time this is basically 0. But as you bring it closer towards the charge, what happens? Now it is coming inside the sphere of this into the influence of this particular charge, right? Now this point when you started is basically VA, your voltage over here, right? Then this point that you're bringing, okay, let's say you're bringing into the sphere of influence over here, okay, VB. Now against this electrostatic force over here, you're bringing it till here. Here, very simple, very easy to move. As it keeps coming, right, the force you have to, the work done in moving the charge over here from here to here is easy. As it keeps coming, it becomes, more work has to be applied, more work has to apply to move within the charge from even a small distance until reach here, even more work has to be applied, right? From here we can say the potential at VA is basically 0, but there is some potential at VB, right? So total V is equal to what? It will be VA plus VB, right? But VA is 0, right? So VI minus VB, so VB minus VA, right? VA is basically 0 over here, so it will just be VB. This is equal to what? Work done in moving a charge, from somewhere from infinity into this field of influence because of this positive charge, right, into this electric field lines around this positive charge. So that is basically your electrostatic potential or your electric potential. Now the electric potential at a point in an electric field is basically defined as your amount of work done in moving a unit positive charge. Okay, this is just a unit positive charge from somewhere from infinity, right, from infinity to the point, okay, to that point, right, in the field, right. This is again into the field of this into the influence of this positive sphere, right, because there is an electrostatic repulsive force acting over here. You have to do some work to move it inside this direction, right. So again, from infinity to that point against the electrostatic force is basically called as your electric potential. So within a field, within the field, if you're moving, right, from here, if you're moving within the field, in this sphere, it is there in the influence, right, here itself, the test charge placed itself is in the influence of the source charge, or because there is an electric field line, it is already in the electric field line, because of this source charge has an electric field line, and this test charge is already in the field line, and on the field line, if you want to move from one point to another, that is potential difference. But from where, from infinity, if you want to bring it into this sphere, into this electric field line, right, somewhere from infinity you're bringing into this electric field line, then this is basically your electrostatic potential. Now if you keep moving the electric field line inside this field line influence, if you're saying to move from this point to this point, what is the work has to be done in moving the unit charge from this point to this point, right, this point to this point, that will be electric potential difference. If you're moving it from somewhere from infinity to here, infinity means the potential over there is basically 0. It is not in the influence of this positive charge at all, right. So from there to here, then it is actually then the work done in moving the charge from here to somewhere into this point over here, right, that is basically called as your, this is basically called as your potential difference. Now the potential difference is again given by the electric potential, okay, at a point is defined as an electric field, in an electric field is defined as the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic force. Now the unit of this electric potential is also volt, okay. Now electric potential is nothing but work done per charge. From here we can say electric potential is basically work done per charge. So here you can define 1 volt, okay. Again this is in terms of volt, right. This is again in terms of 1 volt, 1 joule and 1 coulomb, right. So again over here you can say the electric potential at a point in an electric field is said to be 1 volt if 1 joule of work has to be done in moving a positive charge of 1 coulomb from infinity to that point against the electrostatic forces. So that becomes your definition for 1 volt, okay. So with that, we are coming towards the end of today's class. Once again, class 12, this is basically your upcoming batches. So in case if if you're planning to take a plus subscription, now would be a good time to take, because there is an upcoming batch. This started from yesterday onwards, right, June 1st onwards. In case any classes, the previous classes you have missed, then obviously the class recordings will be available for you. You can watch the class recordings and come back during the doubt classes. You can ask the doubt. So physics I would be taking, we meet every Monday, Wednesday, Friday between 5:15 to 6:15. Chemistry Manisha ma'am will be taking, Lakshay sir will take biology, and math Jyoti ma'am will be taking. Now for the target of this course is basically a completion of your midterm syllabus. So we will be concentrating on your term 1, that is your term 1 syllabus for the first 5 units of your syllabus. So that and you can, again, if you're planning to take a plus subscription, this again you can use my code MTIS10 to avail a 10% discount. And don't forget about the special classes that are coming on for class 12. There is a special class on 10 on tomorrow, or on 4th, and class 11 there is a special class in the Unacademy platform tomorrow onwards. Now we also have the UNSAT. The UNSAT is basically in case if you're trying to take the class IIT JEE or NEET UG, or in case if you are in class 9 and 10 and want to take foundation courses, right, then you can actually make use of this scholarship test. So this will be an offline test that is basically conducted in the Unacademy centers, like offline centers, and it will be a computer based test. So this is happening across 40 cities. So last stage of registration is today. So if you haven't done it, now would be the great time to register. And you can the test will be on June 4th and 5th. So top 40 rankers will win an iPhone, all test takers will get a t-shirt, and in case if you have depending on how much percentage you're taking, whether you're coming in the first 5%, first 10%, right? Depending on that, you will get scholarship up to 90%. All right. Now, again, to the test, the registration fees is around 199 rupees. You can use my code MTIS10 to avail a 10% discount on the same. Okay. So any more questions about this, you can drop it in the, you can ask, if you have any more further doubts, you can ask in the chat box, right, regarding the unsat. And we are introducing the community feature. So my community link is actually given here. So you'll never miss any update from your favorite educators in case if you're following their community, and you can share your feedback and directly with the educators via pools as well. Okay. And if you're joining my community, there'll be a few questions, pool based questions, right? MCQs I would have asked, you can try giving them, you can just try those questions, right? And in case in any of the videos, if you're seeing any inappropriate content, and if you report the same, you can claim a prize. Okay. And like and share the video if you like it, right? And also click on the bell icon to subscribe to the channel, so whenever the next class is there, you would be updated regarding the same. And thank you for taking the class, and in case if you have any doubts, you can ask me in the chat box, or else I'll be ending the session now. All right, thank you.